All right. So our last speaker of this first invited talk session is Julie Adams, Dr. Julie Adams, who is also joining us from Pacific time zone. Thank you so much. She is the Associate Director of Research in the Collaborative Robotics and Intelligent Systems Institute, as well as the Professor in the School of Electrical Engineering and Computer Science, and in the School of Mechanical, Industrial and Manufacturing Engineering at Oregon State University. I think she also doesn't need further introduction. So Dr. Adams, whenever you're ready, please take it away.
Thank you. I would ask that if my slides are fuzzy or I'm not coming through, that you let me know. I'm in a hotel, so I'm on my hotspot. So I apologize for that. I wish I could be there. And Jen Khan says hello. So I'm going to talk about human interaction with true swarms in the real world. I was a member of the DARPA offset program in, hold on one second, sorry. Gotta make sure my thing is in the correct place. I was a member of the DARPA offset integrator team, and that's what I'm going to be focusing on in this talk. We care in my research lab about this idea of human collective teaming, and I use the word collective instead of swarms because I talk about swarms as being spatial swarms, so things like flocks of birds and schools of fish, whereas collectives tend to have different roles, maybe like colonies of honeybees, and some of the things that Magnus was talking about. And specifically what we are looking at is how do we actually create a situation in which hundreds or thousands of these cooperative robotic entities that are highly autonomous can team with humans and be responsive to them. So there's been quite a bit of work into human swarm or human collective interaction. Myself, Mike Goodrich, Katya Sakar, Mike Lewis, amongst others around the world. And so, you know, we tend to think about this differently because you are unable, when you have these large numbers of vehicles, to be able to interact with every single vehicle. You see a couple of pictures here. So the picture on the left is a picture of one of our robots at one of our early field exercises in 2018, I think, definitely pre-COVID. And you can see that we're inside of a building. The picture on the right is a picture of our launch zone area at the last field exercise last November. This building that you see with the tent on top of it was the command and control building. I'll talk more about that in a bit. And if you ever want to be in a lovely work environment for 3 weeks where the temperatures range from 20 degrees Fahrenheit to 80 degrees Fahrenheit, live in a tent in the middle of Tennessee. So our team was the command and control of aggregate swarm tactics. Our primary investigator was from Raytheon BBN Technologies in Cambridge, Massachusetts. And along with myself, we were also co-PIs with Smart Information Flow Technologies. You see a picture here from the last field exercise. And while it may be difficult to see on the slide in the room, it's a truly heterogeneous swarm. We have ground vehicles, we have multiple different types of multi-rotor vehicles, as well as fixed wing vehicles. And then in the back here, this is a system that was developed as part of the DARPA offset program in a sprinter project called the Hive. And so the idea here was to be able to launch UAVs from this device more rapidly and provide a smaller launch zone. There are a number of assumptions within this program. So this program assumed at the end of the program, and it ended last June, this past summer, that we would be able to deploy up to 250 vehicles in an urban environment across about a 10-block city area. And you know, in the end, we had a bit of a fire in Cambridge a year ago and lost about half of our collective about 2 months before the deployment. So we only had about 140 vehicles instead of the 300 we expected to have. But we also, throughout the program, had developed a multi-resolution simulator that allows us to do live virtual deployments. And so we actually were using that simulator to deploy during the shifts to play the scenario that we were asked to play. Throughout this program, the complexity of the field exercises grew, as well as the expectations with regard to the number of vehicles, the density of the urban environment, as well the types of tasks that the robots needed to do. However, what I want to be clear about is that this program really focused on the scalability of the swarm and not on the actual development of the robot technology itself or the sensor capabilities. So one of the things in this program was that it focused on using April tags of different complexities throughout the program to act as artifacts in the environment. And some of these April tags, so you can see one on the ground here, and I know for a fact, you probably can't tell, that there's a little box right there, and that box has a Raspberry Pi in it, and that Raspberry Pi has a Bluetooth dongle attached to it. So that means that that's a live artifact with which our vehicles had to be able to interact. And so based on the April tag and knowing what that April tag is, you had to know how to respond to that April tag in real time through your Bluetooth dongle. There were also April tags that would change over time. So they were on a display, and there were movable April tags throughout the final field exercise. So pretty complex situation that we had to be able to deploy in. And so as you would imagine, these vehicles are highly autonomous for deploying this large of a number. If you've worked in human robot interaction for as long as I have, which is over 30 years, and I've worked specifically in multi-robot interaction all that time, you know that once you get past, say, 8 or 10 vehicles, it's almost impossible to interact with every single vehicle. So what do I mean by these types of environments? These are human-built environments. They're definitely intended to be urban-like. Each of the field exercises occurred at a U.S. military-based training facility, urban training facility. These facilities are not in environments where you have cellular coverage. So you often hear roboticists, especially in academia, saying, yes, we can use cellular networks, or we can use Wi-Fi. That does not work in these environments. And in fact, both teams, both integrator teams had to come up with network configurations. In our case, we actually used an LTE base station. The LTE base station is a line of sight sensor, just like your cellular phone. And if you're in an urban canyon or you're blocked from the satellites, you're not, or from the, not the satellites, from the towers, you're not going to have coverage. And so we placed the LTE base station on the tallest building in the captive. And we assume that we are going to lose communication with the vehicles when they drop down. So if the UAVs are flying and they drop down into an area such as right here, this is definitely a dead zone at this particular captive between this narrow street, both for the ground vehicles and the aerial vehicles when they drop down into that area. So you have to recognize that that's going to occur. Additionally, I mentioned the April tags. These April tags are the artifacts are on the sides of buildings, on the tops of buildings, inside buildings, and we were expected to be able to go inside of buildings. These buildings, as you can see from the picture on the right, are multiple stories in some cases. In theory, we were supposed to be able to go up the stairs with the robots. That was not always possible. And you were expected to be able to play the scenario in all the different environments that one would encounter. And what that means is you have to be able to transition seamlessly from GPS to GPS denied environments when you go indoors, and then transition back. Additionally, what this means is that when the vehicles are inside of a building, you have no communications with them, so you don't know what their status is until they come back out. So on the left here, you see this bird's eye view of the area that was in play. These trees were not in play, but these buildings over here were, so they get stuck in the image. And so you can see that there's about 50 buildings here. It's a very dense environment compared to the other environments that we had deployed in for prior field exercises. And the blue area here is where we were restricted to putting our vehicles for the launch. Originally, DARPA wanted just this blue area down at the bottom here to be the launch zone, which was far too small. And we ended up being able to use the road and then this little area on the left. However, what you can't see very well is that there are power lines right here. And, you know, this is well, actually, you can see it in this picture right here, because that's right in front of the C2. And so, you know, you've got power lines, light poles, et cetera, that you have to know are in the environment. In our case, we develop a digital terrain map and we create obstacles because we don't have sensors on the vehicles to be able to detect things like power lines. Our command and control area is this yellow building down here at the bottom. And it is a situation where the swarm commander is unable to directly see what's going on. Our vehicles are commercial off-the-shelf vehicles. And while I agree with some of Magnus's points, there are lots of situations where you are not going to have very intelligent vehicles because you are unable to spend a lot of money. The most expensive vehicle here is the Vifi EFO, which was about $3,900. And this was with additional technology put on these vehicles. You might be surprised, many of you who know the 3DR Solo, but let me tell you, that's one of our best vehicles that we had in our swarm. It was also the cheapest, and it simply had a Raspberry Pi on it and a Pi cam, along with the antenna for the LTE base station. It was exceptionally good for what we needed to do. The types of tasks that we're doing in this situation are trying to surveil buildings, such as what you're seeing with the Solo on the lower right. So when we do a building surveil, for example, we send out a subgroup of vehicles where some of the vehicles have a forward-facing camera and are coming down into the built environment and are looking at tags on the sides of the buildings, while one vehicle, typically one vehicle, has a downward-facing camera and is looking at the roof for additional intel. These missions are typically a 3-phase mission, where the first phase is trying to gather information. The second phase is using that information to gather more intelligence and to identify where your high value target is. And then the final phase is trying to locate and cordon off the high value target. We typically use a mission plan that has multiple nodes that can be activated. Like I said, these are highly autonomous vehicles, and we do high level tasking. The closest thing that we would come to a low level task, if you will, is a go-to or a nudge. And in the case of a nudge would say to that UAV, for example, move up X number of meters. And if it were a ground vehicle that was being nudged, it'd be move forward in a particular number of meters that are pre-specified before the mission deployment. So we faced a number of issues when developing the commander interface for the swarm commander. And if you look at the typical types of things that people use for control stations, we just really weren't going to be able to address with a two-dimensional interface these particular criteria. So when you have swarms and subgroups of swarms, it's very fluid. The swarm members can change as well. Like I said, you're not going to be able to interact with every vehicle in that large number of vehicles that you're deploying. And so you really have to be able to look at a higher level type of commanding and commanding groups, subgroups, or the overall swarm. You also have these mixed capability vehicles. So you saw the number of UAVs we had. Even though we had all those different UAVs, the Vifi EFO over here and the little modal seeker were the two UAVs that were specifically designed to be able to go inside of buildings. The modal, the Voxel and the 3DR Solo were not. As well, the ground vehicles could go into buildings. So you have a lot of heterogeneity, even though for a lot of the typical tasks like the surveil, going out and trying to interact with particular artifacts in the environment can be done by any UAV, and it's treated that way. You do have some tactics for which you do need specific capabilities within the vehicles. There's also this very vertical aspect in this urban environment that you have to address. So if you have a 5-story building, a ground robot, and the Ion R1 robot is not a very big robot. It's about 18 inches long and probably about 12 inches wide. So, you know, it is an outdoor environment. It can go over some curbs, but not all. You know, it is not going to have the capacity to be able to identify April tags that are on the 5th story of a building or the top of a church. And so you have to have the UAVs come down into this environment. So you do have to be able to get that perspective in order to be able to understand how to set the goal points for the tactics that you're establishing. The other aspect here is that you've got this very large volume of space. And so you have to also be able to understand kind of what your density of vehicles is around the different areas of the space relative to the density of the obstacles. And so that's an aspect that really needs lots of different perspectives to understand. And then there's scenario elements, some of these artifacts that really require that multiple perspectives. So for example, I'm going to show you a representation in a moment of an explosive device. And an explosive device only needs a single vehicle that has the appropriate payload. And these payloads are virtual payloads. So an electronic payload can detonate a bomb. A munition payload can take out an adversary of a particular nature. And so there were in the final field exercise some of these adversarial artifacts that required coordinated simultaneous interaction with submembers of the swarm with the artifact. And so in order to be able to place that appropriately, the goal points appropriately, and to manage ensuring that you have that simultaneous interaction, you really have to have something different than your typical 2D display. The final criteria is that our swarm commander is near the battle. So this individual is not down in the urban environment. They are in a command center. And so we really needed to develop some sort of immersive environment to allow them to understand this entire thing. So the Swarm Commander interface is called I3, which was developed by SIFT with a lot of input from myself. And so this picture on the upper left, you can see one of our Swarm Commanders. We use the Vive virtual reality system. So he's got the headset on, he uses the hand controllers, and there's also a chest tracker that is used to display some information on the peripheral sides for the Swarm Commander. This image in the middle here is an example of what I was talking about with the bomb. And I want to just point out that the magenta circle here is what the Swarm Commander can actually see in the virtual environment. So it's much smaller than what I would see on the screen. So this particular bomb has been located. The artifact has been located. And you see this lighter red circle, which is really representing how close a robot can get to this before it is neutralized by this bomb. And so we want to be able to get the vehicles as close as possible to that to activate the payload in order to neutralize the bomb, as opposed to having ourselves neutralized. If a vehicle becomes neutralized, they have to return to a medic in order to be revived. In the upper portion here, what you're seeing is that we're actually deploying the swarm, and these different colored balls represent tactics that have been assigned to submembers of the group. When the tactics are assigned through the mission planner and the dispatcher, then they are assigned to the appropriate vehicle with the appropriate payload that is closest to the goal point for the specific tactic. The Swarm Commander can issue tactics at a high level as well, such as the surveil tactic that you see in the lower picture. And in this case, the Swarm Commander can also do that in a way where the vehicles are automatically assigned to the tactic, or the Swarm Commander can actually select the vehicles that are on the launch pad to deploy for that tactic. It just depends on the situation. If we're really busy, then we're using the mission plans, or we're doing tactics where the dispatcher automatically selects the appropriate vehicles. And I mentioned the live virtual before. When we do live virtual, there is no difference to the Swarm Commander other than a little icon on the vehicles to represent the virtual vehicles, distinguish them from the live vehicles. So we have heads up displays that gives us counts of how many vehicles are active. So this is how many quad rotors are active, how many are not in communication, and how many are assigned a tactic. This is the number of rovers similarly. And then the fixed wing vehicles were developed by Johns Hopkins Applied Physics Laboratory, again, as a sprinter. We did not have control of them at the field exercise, but they could be deployed during our shifts, and they would show up in this heads up display, and their telemetry would show up in our interface. So in our last field exercise, I was able to actually do a sort of a human subject study, the first of its kind. We have 2 swarm commanders. They are CCAST members. As you can imagine, we do want a lot of training for safety reasons, and they are, experts at what they do. We generally split the shifts for which we did data collection as evenly as possible across them. And so this is just an example, again, of our swarm commander. So this side of the table, the left side of the table, is the entire system other than the tripods for the Vive system for the i3 interface. And this whole side with all the stuff, which is on the right-hand picture here, is my setup with all the sensors that we use to collect our objective data. And this computer here with a little note on it is collecting all the physiological information. And then the second computer is being used to collect subjective information and record that information. Over the course of the field exercise, we did data collection from November 11th to November 18th. And you can see this table is a little bit of an eye chart, I know, but I'm trying to show you that how many vehicles we're deploying of different types. On November 11th, we were actually only in simulation because we were in the hotel because of rain. But you can see that for hardware wise, we had all 140 vehicles. We had 140 vehicles. We had more than that when we got there, but we crashed some. And then we also had 50 virtual for that final field exercise. The 17th, this one that has lots of different numbers going on, we had wind gust up to 29 miles an hour and actual sustained winds at 26 miles an hour. So we intended initially to just test out each of our vehicles because we'd never flown them in that kind of wind before. But the wind started causing problems with the LTE. So we had quite a period of time during which the LTE was going up and down. So we brought up the simulated agents. But we were being very careful because the LTE would come up and you could potentially task the live agents with that. So lots of interesting challenges. I can talk for a long time about that. At the end of the field exercise, so on the 2 p.m. shift on November 17th and then November 18th shifts, DARPA told us like 2 days before that we were going to do joint shifts with the other integrator team. So that meant that we split the CACTIF in half. We had one half, they had another. And for the first two joint shifts, we just had a single operator, swarm commander. But we decided on the very last shift, which was going to be the very last shift ever for this program in this context, that we were going to have 2 swarm commanders. And so we did that. And it worked out actually quite well. Where one really was doing the mission planning and one was doing more of the tactic deployment when we needed to do tactics. So, I've kind of glossed over a lot of things that I'm not yet approved to distribute and to talk about, but I can tell you that we finally do have evidence that a single human can supervise a swarm of 100 plus real robots. And in fact, when we looked at the overall workload data, we found, and this is the objective data, that their data was in the 92% normal, was in the normal range, 92% of the time. And that's over 12,000 data points from this data collection. Both swarm commanders had overload conditions and the highest frequency was about 16%. So this data really confirms what we had seen as a team over the last 6 years now. And this is the first known objective workload data set. And we have hopefully some journal papers coming out soon on this. And I have like 2 minutes left for questions, sorry.
Thank you very much, Dr. Adams. I think there is a question on Slido. So let's start with that and then we'll take questions in the room.
Okay, I closed Slido because I was having problems seeing.
Yeah, no worries, no worries. I'll ask this question as if I was this anonymous from Slido.
Thank you.
So in terms of communication within the swarm, were the groups separated by network? And was it challenging to manage networks given the fluid groupings?
No. So there are no networks, no networks within the groups. So the vehicles are unable to communicate directly with one another. They could sense one another, but they would not be able to do moving obstacle avoidance, if you will. all the communications have to go through the LTE base station back to the dispatcher program that I had intended to talk about and I forgot. The dispatcher is a central program that brings in the telemetry, brings in the information from the vehicles, and then sends those vehicles information about other vehicles in their area, but does not, the vehicles themselves don't directly communicate. That was beyond the scope of what we were required to do and what we were asked to do. And quite frankly, they didn't give us enough money to do for this project.
Hello, thank you very much for the amazing presentation. It's really very, very impressive. I wanted to ask about how you were doing the assessment on the human operators. You mentioned in the end that how their workload was managed and what was sort of like the data set that you were talking about.
Yeah, so I have algorithms that I've been working on for about 15 years for doing multidimensional workload, overall workload assessment that focuses on the different components of workload. And so we use sets of physiological metrics. So we use heart rate monitors and let's see, microphones. Typically we use an eye tracker, but not in this case. We use a noise meter and some other sensors. We do not use EEG. EEG is not appropriate in our environments because our supervisors are moving around and EEG is not useful in that domain. We also do not use FNIRS, although I will say the other integrator team did try to collect data with FNIRS. And I'm not quite sure how successful they were. I know that they haven't been able to publish anything yet on that. And I don't know that they actually got enough data to publish. So I have a lot of papers on that. If you would like to look at those, I point you to my Google Scholar.
Yeah, definitely I will.
That's entire other talk.
Yeah, I can imagine. And do I have time for another question? That's all right. No worries. Thank you very much.
All right, let's thank the speaker again.
Thank you.
Thank you very much to the first three, for joining remote. I think we'll continue with the interactive session next, and then we'll have in person.